Hi folks, welcome to the next lecture, and in this lecture we're going to take a look at exponential growth. In the following lecture we'll take a look at exponential decay. It's the converse. So again, just to reiterate, an exponential function, how you define an exponential function is the power is where the input lies. That's the bit we control or we change. We change the power, and that has significant impacts then on the behavior of the function. So the base is a constant. So people often think that an exponential function must be defined by e, but it's not. Any base with an input that's variable is exponential by definition. 1.6 to the power of b. These are all exponential functions. Just this function by definition is always exponential because it's always written with a variable power, whereas 2 doesn't have to have a variable power necessarily. So the base is constant, the power is an input. That's our definition of an exponential function. Remember, linear function, the base was what changed. Quadratic, the base changed. Cubic, the base changed. Reciprocal, the base changed. Now we're looking at the base doesn't change, but the power changes. That's the difference, and it's significant. There's a few conditions. A can't be equal to 1. Otherwise it makes no sense, because 1 to the power of any power would always be 1. It must be a positive value, and x is a real number. Real is a mathematical definition. It can be a fraction, it can be a decimal, it can be positive, it can be negative. So a function like this always has positive outputs because a is positive and x is real. And a positive base raised to any power is always positive. So even if we have a negative power, if we have, say, 2 to the power of minus 1, that's still a half, which is still greater than 0. So a typical graph of a growth function looks like this. So this is 2 to the power of x. The slope is always positive. And as x gets bigger, the slope is always changing and it's always becoming more positive. So the slope is continually changing, which can be quite difficult for analysis, but we'll work around that as we move along. So just in general, I mentioned this in the last lectures, but it's really important to reiterate it, is the sign on the power. So the sign on our input determines the nature of the function. If the power is positive, it's a growth function. So here x is a positive value, and it gives us this typical graph. If the power is negative, it's a decay function. And again, it has a typical graph. So the main difference, guys, the function can be written with loads of different letters, as we'll see as we move along. But what you're really looking for is the power on the, is the sign on the power positive or is it negative? So the general equation looks like this. This is the kind of general maths equation. We look at the more specific science one very shortly. This is the typical graph. And these are just some examples of exponential growth functions. There's lots more of them, but these are the kind of typical ones, the most common. So now, in science, we tend to use a slightly different formula. It looks completely different, but it's exactly the exact same thing as the last one. Sorry, I'm writing that wrong. So the previous function we looked at, the general maths function, looked like this. And they look completely different, but the main thing is, guys, they're actually the exact same. It's just the letters have a different meaning in a scientific application. So here, N0, now that's just N with a subscript, N0. That's the original conditions, that's the initial conditions. T is the time, and N is the new value. So we have, usually in the question, to be given the initial conditions. You know, a bacteria started with a population of 24. It grew to 48, and you'd usually be given a timestamp as well. This all happened in 2 hours. Now K is the critical bit, and we're going to devote a couple of slides to K very shortly. K is the exponential growth rate. So in this case, it would be the growth per unit time. And we always have to calculate K first of all in any problem. That's always our first job. K is the equivalent, kind of, it's like the slope. It's very, very important. It's essentially the engine that drives the growth. So this is just a general scenario. These are just general letters. Very often, if we were looking at bacterial population, we'd be talking about a count, and the equation would look like this. So the letters will change all the time. Sometimes it would look like this, with a lambda instead of K. So just be prepared for these equations to continually change their appearance. But the main thing you're looking for is, what's the sign on E? Is it positive or is it negative? If that sign is positive, you're looking at growth. If it's negative, you're looking at decay. And again, these are usually represented with a growth curve. Very important to get familiar with the shape, this kind of slow start, and then a very quick acceleration. So what is K? K, as I said, K is the essence of the function. It's the engine. This is what drives the rate of growth. It's the rate of growth per unit time, the exponential growth constant. Small changes in the value of K can have significant impacts on the outcome of the results. We'll see this on the next slide. This is important as well. In most questions, you'll never be asked directly for K. Now, in my questions, I do, just to kind of bring it out as a separate task you must complete. I would always have calculate K first. But when you look at the quizzes, you won't be asked for K, but you will need to calculate it. So if you're not calculating K first, you will never get to a right answer. That's essential. So if we look at K kind of just in a general context, a good example is to compare it to the rate of interest that a bank could offer you. Say if you've invested money in a bank, K is the equivalent of the rate of interest the bank is offering you. So we just take a look. K should always be positive. So it should be greater than 0. And just here we have two kind of 100 euros is invested in a bank. And the blue curve is looking at if the bank was offering 3% interest. In this case, remember we never use a percentage in a calculation. In this case, K would be 0.03. The red line is 4% interest. So K is 0.04. And just to give us an idea, say if we were asking how long would it take for my investment to increase to 1,500 euros, at 4% it would take 64 years, at 3% it would take 90 years. So just that 1% percentage difference in interest over time, as we can see, has a significant effect on the rate of growth. So very small changes in k have significant impacts on the steepness of the curve and the rate of growth. So for this reason, we always calculate k to 5 significant figures. Always, always, always. So make sure you always calculate k. So that doesn't matter how many zeros they are. It could be very often, but you need to have 5 more figures here after the zeros. And now we're going to take a look at manipulating the function for k, because you always have to do this at the start. So I've just laid out the manipulation in detail. The exact same manipulation applies for t. We just take a slight change at the very last step. So we'll take a look at both, because usually I would ask you, you'd need to calculate k first, and very often a question would ask, how long will it take for the investment to grow to 2,000 euros or 3,000 euros? So we need to be able to isolate t as well to get time. So we need to manipulate the exponential growth formula, this one. And we want to get k on its own. So we need to strip away n0, then we need to strip away the e, and then we need to strip away the t. So the order in which we do things is critical. So our first step is we're going to divide both sides by n0. Now we want to kill the e on the right hand side, so we get the natural log of both sides. Remember the natural log, log to the base e. That's what kills any base of e. So we get the natural log of both sides. Now there's no base holding up the power, so the power just drops down. We have kt. Now we want to get k on its own. So first of all, if we want to get k on its own, we divide both sides by t. And this now is the function for k. Similarly, like I was saying, if we want to get t on its own, then at this step here, we divide both sides by k. And that's the function for t. So in any written work, you would always be expected to go through this manipulation first. You don't just produce the function and drop it on the page. You would always be expected to start with the general equation. You'd be given that in any exam scenario. And then you manipulate down to get k, and similarly you would manipulate down to get t. So just be aware of that. In science, you're always expected to show you understand what you're doing, that you're not just learning formulas off by heart. So we're going to use both of these functions in the following questions. So I'll just kind of drop them onto the page. I won't go through the manipulation each time, but it's very important to understand you're expected to be able to do this manipulation. So we're going to look at a spread of disease problem. So the spread of disease is an exponential function. The infection rate determines how quickly the disease is spreading. So this is just looking at some examples. So measles is very contagious. And we're currently experiencing COVID-19, which is also contagious. It's not as contagious as measles, but the rate, the infection rate, you often hear that, that's often called the R number. How many people does one infected person infect? So measles is very contagious. COVID, the R number can kind of vary quite a bit depending on the suppression measures taken by the government. So that's one example of exponential functions. We'll just go through a few of these first and then we'll look at the maths. Sorry, I thought there was an example coming up now, but these are more just general examples of exponential functions in the real world. Bacterial growth is another example. Bacteria and viruses, they grow exponentially when suitable conditions are present, the right temperature, the right type of food, the right conditions. Again, you guys probably know more about bacteria and viruses than I do. But here we can see some bacteria growing exponentially. And you can see it starts off slow, but then suddenly there's this very, very quick acceleration. And this is the typical example of natural growth that E governs. Here's a same again, but this is shown on an agar plate. So these are both examples of exponential functions at work. Nuclear fission. So this is where either a nuclear reaction, a controlled nuclear reaction, which is what would go on in a nuclear reactor, like for generating power, that's controlled nuclear fission. So what happens here, the diagram might be a bit quick. So one neutron is fired at a uranium-235 atom. So what happens then is this splits into two different masses, two smaller atoms generally. They can be of various configurations. But the big thing that happens is 3 more neutrons are fired off. In general, on average, it's not each time, but on average, 3 more neutrons are released when this split occurs. And each of these neutrons go on to hit the next uranium atom, and we get this exponential function. So the 3 is because of the number of neurons that's released. And then either this reaction is controlled, that's what will go on in a nuclear energy reactor, or it's uncontrolled, and that's what will go on in a nuclear bomb. So this develops into then what's called a chain reaction. Now it's not very clear here, but this is kind of showing you how one split very quickly, neutrons are fired off, and this causes what's called a chain reaction. Obviously we don't want a runaway chain reaction within a reactor. That's what happened in Chernobyl back in '86. But in a nuclear bomb, this is what's exactly going on, this huge release of energy. So as well as the neutrons being given off with the split, there's a huge amount of energy released as well. And we either ideally trap that energy for useful purposes, or in a military sense for destructive purposes. There needs to be also what's called a critical mass. We need enough uranium-235 atoms around the atom that's been split in order for the reaction to sustain and continue. So these are all exponential growth scenarios. Compound interest is another example of exponential growth. We kind of looked at this briefly with the discussion on K. And this just gives an example again of kind of say €1,000 invested at different percentage rates. And you can see a small change in percentage has a big impact on the amount of money accrued. Say, oh, this looks like 20 years. So at 5%, we would have, if you invested, say, €1,000 at 5%, after 20 years, you'd have about €2,600 saved or in the bank. Whereas if you did the same at 10%, you'd have over 7,000. So just bear that in mind when you're either borrowing money or kind of investing money. What seems like a small amount, a small difference in percentages, you know, oh, will I get a mortgage that's 3% or 3.25%? It mightn't seem like much, 1/4%, but when you extrapolate that over 20-25 years, it can be a very large amount. And that's because of exponential growth. Remember, these are actually the K figures. So K would be 0.1 here, and K would be 0.05 at the bottom. So those are all examples of exponential growth. You'd always be expected to be able to kind of, you know, at least 3 functions, 3 kind of scenarios where exponential growth would occur. We've looked at 3 there. There's many, many more. The growth of human population, our rate of consumption, how much we consume material, has grown exponentially, as well as the population, which is why we're in the kind of crisis we're in with the climate. And this just gives an example then of kind of what happens if you don't, different types of, this is your principal, this is the amount of money invested. This is just the same slide again, kind of, but just a bit more detail. This is interest with no compounding, where if you just got 2% per year. And then you can see compound interest is the big one. So compound interest is exponential. Interest with no compounding is linear. That's a linear relationship. So obviously if you're investing, you'd like to be getting a compound interest return. If you're borrowing money, ideally you'd like interest with no compounding or no interest, but no bank. This is where the banks make their money, obviously, as they compound the interest on your loan. So now we'll take a look at an example. So the number of people infected with the flu virus follows an exponential growth phase. Initially, 15 people have the flu, and within 2 weeks, 95 people are infected. So the first line of most questions will give you enough information to calculate K. And this will always be your first task. But we'll take a look at this as we will take a look at the question in full. But the first sentence in the question, you should be able to calculate K from that, because we have the initial condition, we have the new condition, and we have the period of time it took for this to occur. Determine the value of K to 5 significant figures. We'll do that first. How many people would be infected after 6 days? So because this question has days in it, when I'm calculating K, I'll actually convert my weeks into days. So I'll use 14 days there rather than 2 weeks. Just to avoid all kind of writing 6/7 as a fraction and stuff, that gets very messy. So always kind of, before you start, make sure you've read the whole question and bring all the units down to the lowest kind of, if it's time, take a look. And if you've got hours and seconds, bring everything to the lowest value. Bring everything to seconds. In this case, we have weeks and days. So we'll kind of discuss everything in terms of days. And now, how long will it take before 200 people are infected with flu? And this, we cannot work out these. Unless we've worked out K, we cannot work out either of those answers. And it's vital to understand that. So this is the function that governs what we're doing. So first step is we're going to calculate K. Now this function, when manipulated, gives us this. I've already discussed this earlier on in the lecture. And now we're going to feed in the values from the first part of the question, like I said. N0 is 15, N is 95, and T, like I said, is 14 days. Feed this into your calculator, and remember you need to go to 5 significant figures. So here we have 5 significant figures. And just to kind of put a bit of sense on this, what does this mean? It means there's a 13.2% increase in number of infected people per day. So that's what K is giving us. It's the rate of growth per unit time. So it's always good to take a pause here and kind of say, right, what does this mean in terms of the question? So this is part A, answered. And again, have to emphasize it, very important, 5 significant figures. How many people will be infected after 5 days? Well, now we're just using the exponential growth function because it's kind of written the way we want it to be. We don't know N, but we do know the initial conditions. That never changes. That's always going to be 15 for this question. We do know K because we just worked it out, and we do know T. So the initial conditions is 15, k is this. So in the question, these two values will never change. Once you've calculated k, it's never going to change. It's the rate of growth per unit time. And t, in this case, is 6 days. Feed all these values into the formula. And when you get your calculator, after 6 days, we would expect 33 infected people to be infected. So that's part B answered. Again, this would be rounded correctly, to the nearest whole number. C, how long will it take before 200 people are infected with flu? So now we need to manipulate this equation for t. And again, I did this back a couple of slides. And this is the function we had. So it's very similar to the k function, just t and k have swapped positions. And now we know this is the new value, this is n. The initial conditions are still the same, and we know k. So we know n, we know n0, and we know k. 15, how long does it take to grow to 200? We could put any number in there, but it's 200 in this case. And k we've already calculated. Make sure you never use a percentage as k. Always convert a percentage value into a decimal. But we've discussed that before. Feed these in, get your calculator, and it would only take 19.6 days in order for 200 people to be infected. Usually the question as well will specify whether to bring it to 1 decimal place, 2 decimal places, etc. So now, a couple of questions just for you to try. So Mary invests 5,000 euros in the mystery bank. After 6 years, her investment is worth 8,650. So determine the value, or k. The reason why it's a mystery bank is because we don't know the interest rate they're offering, and that's what we have to calculate first. What's k? So again, guys, there's our initial condition. Initial conditions. There's the new value, and there's the time. So you use the formula for k, or manipulate the original formula to get the k formula and feed the values in. What will her investment be worth after 10 years? And how long before the investment is worth 25,000 euros? So the pattern is the exact same as we did in the previous example. But whatever you do, make sure you calculate k first. Another example here now. A bacterial population follows an exponential growth. If the initial count is 56 and this grows to 142 over 48 hours, we now need to work out k. Just CFU, guys, to explain CFU. CFU is colony forming units. So you'll come across this when you're working in labs and you're doing your microbiology and stuff like that, is when you inoculate an agar plate here, so this is a plate before, just as it's been inoculated. As time passes, whatever you've inoculated with, they often form colonies, these little dots. And they're the colony forming units. And as time passes, both the size and number of these dots increase. And eventually they nearly increase to such a size that it becomes impossible to count. So a plate count should be between 30 CFU and 300 CFU to get a successful plate count. But I let your micro lecturers talk you through that. This is way beyond my pay grade to discuss them, other than to just introduce the meanings of what CFU is. So CFU is just, it's a count. You literally, every 6 hours you might come back and count the number of visible dots on your agar plate. And it's called, imaginatively enough, a plate count. What would be the expected count after 72 hours? And how long would it take for there to be a count of 280 CFU? So even though the scenario is completely changed, we looked at a flu virus, we looked at investing in a bank in question 18.1, and now we're looking at bacterial populations. The maths, the process, the mathematical process is the exact same. From your initial part of the question, calculate K, and then you can answer part B and part C. On the quizzes in Moodle, you will not be asked to calculate K. You'll just be asked either this question or that question. But you must calculate K first, otherwise you won't be able to progress. So we finish up there, guys, for exponential growth. We'll be doing similar examples when we look at exponential decay, but that's the business of the next lecture. So thanks again for listening, guys, and we'll chat to you again soon.